All right, let's get started. So good afternoon, welcome everybody. My name is Sonja Schmid. I'm a faculty member in the Department of Science, Technology and Society at Virginia Tech. And it is my pleasure to welcome you to the 18th SIREN event of the series. SIREN, the seminar on interdisciplinary research and education on nuclear emergency response. The series is part of my NSF Career Award on globalizing nuclear emergency response. And in the spirit of this type of grant, we emphasize the importance of both research and education in the area of nuclear emergency preparedness and response. So all SIREN speakers are meeting with graduate students as part of their engagement, and we plan to provide access to a recording of these lectures. SIREN is generously supported by Virginia Tech's Office of the Vice President for the National Capital Region. Many thanks to the staff of the Virginia Tech Research Center's Executive Briefing Center and the IT team for their support, and to the students, staff, and faculty in the Department of STS for helping to make this happen. Today's talk will be live streamed. We have about 30 remote participants signed up as of this morning, and these attendees are joining us not only from our main campus in Blacksburg and other U.S. universities, federal agencies, and national labs, but also from abroad. So welcome, everybody. If you're watching us online and would like to submit a question to our speaker, please send an email indicating your name and affiliation to SIREN, S-I-R-E-N, at vtvirginiatech.edu. And also, if you'd like to be added to our mailing list, we use it only to announce SIREN events. You can join our new Google group. If you look for it, SIREN series, you can submit a request to join. You can also leave the group if you no longer want to receive announcements. And I just want to make one quick announcement for the next series. The next event in this series will meet again on November 2nd, and our guest will be Alex Wellerstein from Stevens Institute of Technology, who will present his new project, Civil Defense 2.0, what would, could, or should civil defense look like in the 21st century. And now it's my pleasure to introduce our speaker today. So Dr. Thomas Wellock is the institutional official historian at the U.S. Nuclear Regulatory Commission. At the NRC, Dr. Wellock writes scholarly and popular history on the regulation of nuclear power. He's currently at work on a history of the use of probabilistic risk assessment in the regulation of nuclear power, and recently published a scholarly article on the topic, A Figure of Merit, Quantifying the Probability of a Nuclear Reactor Accident, in the journal Technology and Culture. So I thought, how fitting, let's invite him to speak to us in SIREN. Prior to coming to the NRC, Dr. Wellock worked as an engineer at the Davis-Besse nuclear power station and as a reactor test engineer on Los Angeles-class submarines. After earning a bachelor's degree in mechanical engineering, a master's and PhD in history from the University of California at Berkeley, Dr. Wellock was also a professor of U.S. history at Central Washington University. He published 2 books. One is called Critical Masses, Opposition to Nuclear Power in California, 1958 to 1978, and Preserving the Nation, the Conservation and Environmental Movements, 1870 to 2000. So you can see that this is the true historian who always adds a time range at the end of the title. He has also published numerous articles on the history of nuclear power and environmentalism, including one on the NRC's role in determining the safety of Soviet-designed reactors in the former Eastern Bloc countries when these countries joined the European Union. Tom has been a wonderful colleague for many years. We've sat on a number of conference panels together and reviewed each other's work formally and informally, and he's currently helping one of my grad students locate documents to examine the NRC's reactor life extension program. We're very fortunate to have him here today. Please join me in welcoming Tom Wellock.
Okay, hello. Thank you, Sonia, for inviting me. There's a kind of, I want to tell a story about Sonia. She mentioned the article I wrote on post-Soviet era efforts to make nuclear reactors safe in Central and Eastern Europe that I wrote. There was a part in there where I kind of criticized something she had said, and I felt very bad about it. And one time we got together, and I confessed to her that I had this article coming out, and it was going to have a paragraph where I challenged something that she had said. And I can remember she nudged me and said, I was the referee for the article. She had read it and commented on it. I had no clue. So Sonia is a wonderful colleague. She really understands the process of academia and challenging each other and each other's ideas. So thank you for bringing me here today. Okay, figure of merit. This article that I wrote is published in the journal Technology and Culture. Is kind of like the first half of what I've been developing in this book, so it's kind of a condensed down version that I'm going to be giving you today. So it really goes back. What I'm looking for in this article was kind of the origins of probabilistic risk assessment, where it came from in within the Atomic Energy Commission, the background on it, and what led to what's considered the seminal kind of PRA, the text of risk assessments, WASH 1400, which was published by the NRC, but really developed during the period when the Atomic Energy Commission existed up through 1975. And so it comes, WASH 1400, also known as the Rasmussen Report, the Reactor Safety Study. It's considered the major risk assessment ever really done and set the standard for what came after it. So I'm going to talk about the development of that today and then talk a little bit about some of the influence that the development of risk assessment in the Nuclear Regulatory Commission had in some other areas that you might not think about. So the problem, though, with this, with giving you this presentation today is if you've ever tried to look at WASH 1400, it is one of the most tedious reports ever put out by the federal government. That is saying something. It was so tedious. There was a review committee of physicists who obviously know their stuff that went through it and said the report was inscrutable. The person who gave the presentation about their critique of the report said that it made him want to engage in heavy drinking, trying to go through it. And so I'm thinking, how do I present this topic to you in a way that is more engaging? How do you take, it has a dull blue cover. This is the most exciting thing about this report, is the blue cover. How do you present a report that looks like this on the inside, and this, and this, and this, and this, without turning my audience into this? Okay. That was my challenge. I hope at least I get points for trying today. Okay. But this report was incredibly important. It's still referred back to, it's still debated today. And it's important for two reasons. It was very politically controversial, and yet it did set kind of new standards. So I'm going to try to boil down this report, this massive 2,500-page report, I think 11 appendices, into two major points about it. The first is the methodology that it brought. It's still pretty much used today. It's actually quite simple, despite the 11 appendices. The concept it brought to risk assessment was, it isn't that hard to figure out. This, by the way, lays out somebody stepping off a plane and parachuting to the ground and whether they're going to make it alive. You see here two items, an event tree, which is basically just a decision tree. Things work or they don't work. People either back in the 1960s and 70s tried to develop assessments of risk using event trees, or what you see down below, fault trees, which were a little different, and I'll explain that in a second. An event tree is fairly straightforward. IE means initiating event up there. So parachutist steps out of plane, plunges toward Earth. Things have to happen to save his life. So either the main chute opens, that's the top line up there, and you parachute to the ground and the event is over. Or the main chute does not open. There is still one thing that will save him, and that is the reserve chute. And so you can see here, if the reserve chute opens, success, parachutes to the ground, might hurt his back, but other than that, alive. And the bottom one, of course, is catastrophe for the parachutist. Now, event trees were useful because it's a time sequence. You can watch the development of a catastrophe in sequences. But it doesn't tell you why those sequences fail, right? The hows and the whys. And that's where fault trees come from. So what you see down below, it's kind of hard to see, but there's two what they call gates down there. The kind of rounded ones are called AND gates. This imitates Boolean algebra. And there's OR gates. So in some cases, like off on the left, you got two ways of saving yourself if you're trying to deploy the reserve chute. There's an auto activation device. If that fails, pull the ripcord. Both of those things have to fail in order for the reserve chute to fail. Okay, and then that feeds into determining how a reserve chute might fail. So what's beautiful about this is that it lays out, if you learn what a fault tree does and you learn some of the logic of it, you can walk up to practically any technological system that you don't know a heck of a lot about and see how it's going to fail. It's a kind of language, visual language about how you can understand catastrophes. The other advantage of this, besides helping you understand how something might fail, is that if you plug in probabilities at each of those gates there, you can develop a probability estimate of how likely is it that the reserve chute is going to fail. So you get risk involved in here, and you also get a visual representation of failure. Okay? And so that's what this did. It doesn't seem very difficult, but people either did the top or they used the bottom. Putting them together was the main innovation of WASH 1400. Putting those two things together allowed you to really see it. And like I said, this methodology that they developed is still used, everything from medical devices, the NASA uses it to a great deal. Of course, the Nuclear Regulatory Commission uses it. It's used in a number of areas, chemical processes and the like. It's a methodology that's widely used. The other thing that it really opened up is that especially since this is the 1970s, computers are becoming much more capable. You can plug this in and you can look at a spectrum of different kinds of accidents. I'm going to come back to this, but before this, you focused on maximum credible accidents, a few stylized accidents, a few big ones, and that's how you try to ensure safety. This lets you look at lots of them. Plug it in, put in different variables, play out different possibilities, look at different systems. This really opens up what you can do if you're a regulator, if you're an engineer, trying to understand how a system might fail. Okay? So that's the good side. There was another part to this study that became extremely controversial, the executive summary. Most of it's in the executive summary. This report also had political ambitions. And you can kind of boil that down into two graphs I'm going to show you. As you can, I know the writing is small here, but this graph shows on the left frequency of events. The lines all up toward the top are man-made disasters. So you see airplane crashes, dam failures, fires, and the like. And it's the frequency of events. So it becomes much more likely that the event is going to occur as you go up the y-axis. Okay? And as you can see, the line way down there is nuclear power plants. So they are unlikely. And also the bottom part is fatalities. And you can also see here that the point of this graph is to show that nuclear power was safer than these other kinds of man-made catastrophes. Quite a bit less. This is, you can see that it's a couple of, almost 3 orders of magnitude less than most of the other lines up there. Okay, so that was the implication. There was another, those are man-made disasters. They also said, look at natural disasters. This was also in the executive summary. The part that really got it into trouble was drawing that line through meteorites. You can see that down there, comparing basically nuclear power accidents to meteorites. A number of the commissioners actually cited this likelihood comparing it to meteorite accidents. Although I was thinking about it as I'm drawing this up. This is 1975. Luis Alvarez had not yet drawn up his theory that the Cretaceous period and the dinosaurs went extinct due to a major meteor impact. So you'd have to actually take the meteor line and kind of draw it way out here someplace for large meteorites. It struck me that when they developed that theory in 1981, they had not really considered the full implications of meteorites in this. But at any rate, comparing nuclear power plants to something as unlikely as a meteorite impact, opened it up to a lot of criticism. The problems with this and what were eventually acknowledged is that fault tree analysis and event trees can come up with an estimate of risk, but there's going to be error bands around it that are, compared to these other events, quite large. You don't have a database. You don't have, at this point in 1975, you have no core meltdowns yet. You have no reactor meltdowns. So this is an estimate with error bands around it. And as would come out, the error bands were larger than the report understood them to be. There were some errors, there were problems, and over a period of several years of critique, that came out. And that led the Nuclear Regulatory Commission to not disavow the whole report, but basically walk back their endorsement of the executive summary, which was treated as basically a disavowal of the entire report, at least in the press. And even actually among a lot of the staff of that period kind of took it that way, that the commission was walking back from probabilistic risk assessment, that they were not going to use that going forward. That will change very quickly. They walked back their endorsement of the executive summary in January of 1979, and we of course know that in March of 1979, 3 Mile Island is going to change thinking about safety at the NRC quite a bit. Now, I'm an historian. As Sonia pointed out, I like putting in dates. I like looking backwards to understand things going forward. And so, trying to understand where this report came from in 1975. It's been written about a number of times, and so there's a kind of standard understanding of where it came from. Why did the AEC launch this study in 1972? Congress wanted it for the Price-Anderson Act, by and large. They wanted it because the Price-Anderson Act was a law that provided government indemnity insurance for large-scale reactor accidents. And these kinds of consequence estimates were used as part of the justification for the government to go forward with Price-Anderson subsidization, basically, of accidents. In case of a large accident, they would have to pony up if it was beyond a certain amount. It was also, as certainly understood, that it was an effort to try to convince the public that reactors were safe. Give them a number that they can hang onto that could convince them that reactors were much safer than they believed, and it's something they could compare it to numerically. So this is going to be a quantified approach to what until this point was a qualitative effort to try to convince someone that reactors were safe. They would say things like something is unlikely, the risk is negligible, low. Those kinds of statements aren't numbers, they're qualitative statements. So, and also largely the assumption is that the methodology that was used here, although they did credit them with integrating this, that the methodology that they took was largely from aerospace, which, as you'll see, it was. Most certainly, to a certain extent, but this is where I go. In fact, the first time a fault tree is ever developed is by Bell Labs in relation to ICBM development. This is the first, I believe this is the first public drawing of a fault tree, 1962, that's ever comes out. But this is used to analyze the failure of ICBMs. This is where it comes from. In 1962, it works its way into the airline industry. Boeing uses it a lot. So it's used for commercial development. And it's used in military aerospace applications. NASA, as I'll talk about later, tries to apply it to the Apollo mission. but backs away from it for certain reasons that I'll get to later. Okay, so certainly that, so I'm going back and I have these kinds of understandings in mind. And so it seems to be a methodology that the nuclear industry turned to in the early 1970s and pulled out and started applying. But as I started going back in time, I went back and read reports that are even more boring than WASH 1400. And I found fault trees everywhere, in the nuclear industry, at national labs. This event tree at the bottom, by the way, is a probabilistic assessment of the potential failure of a satellite upon, that a rocket booster will fail, and the satellite will fail upon re-entry, burn up, and you'll have plutonium everywhere, basically. Okay, so this is the probabilistic risk assessment done in that. AEC was involved in that. And others. This is called an event sequence diagram. This also tries to assign probabilities. Sometimes they were creating these things to design something better. Sometimes they were looking at actual quantitative numbers. The industry used it. Westinghouse, General Electric, combustion engineering did it badly. And I just found them everywhere. There are tons of reports in this, going back to the early 1960s. So, okay. I find out that the NRC is basically kind of paralleling, not the NRC, excuse me, the Atomic Energy Commission is kind of paralleling developments in aerospace as far as fault tree development. That's nice. But eventually, of course, the path goes dry around 1964 because fault trees aren't even developed until 1962. Is that the end of the AEC's efforts to develop probabilistic risk assessment? Well, no. One day, I don't even remember why, I was in a Department of Energy database looking for documents on Hanford. And for some reason, I typed in the word probability. And, I forgot, this is a fault tree done by a guy named John Garrick, who's a big name in probabilistic risk assessment. And one of his first estimates for a chance of a reactor failure was 10 trillion, one in 10 trillion. As he said, that had problems with it. But anyway, and I also forgot to mention, this wasn't something that we were just doing in the United States. This is one in Great Britain. The British wanted to do this. The Germans wanted to do it. The Canadians. In fact, probabilistic safety approaches were so much a part of the Canadian system that quantitative risk was sometimes called the Canadian approach to safety. So to get back to the memo that I found as I typed in probability on the database was this one. Evaluation of the probability of disaster. I think this is why if I retire and I still feel like writing history, I'm going to go write about Hanford because they just use great language. They use words like catastrophe and explosion and disaster all the time in their memos. But I'm looking at this. This is 1953. The manager of the Hanford site in 1953 is General Electric Corporation. And they propose in here, as I'll come back to shortly, they propose the evaluation of probability of disaster, an actual quantification of the probability that the Hanford reactors would explode, because they do have that kind of Chernobyl-like possibility to them. So I'm now in 1953. I am 20 years back from the Rasmussen report. And I see that you have people working within the AEC system that have been trying to quantify the chance of a reactor accident, going back into weapons development, going back to the very early period of the Cold War. And so I realized the question isn't why did we develop risk assessment in 1972? But why? What took so long? Why was it 20 years before we actually undertake it? What were the forces that finally came together in 1972 that launches this? And I don't think it's, some of this is fairly obvious. If they always wanted to do it, what had changed by 1972 is that they could do it. Computer development, methodological developments, all allowed them to now think about trying to totalize all of the probability, all the probabilities from various accidents that they could. As they'll discover, it's harder than they even imagined. But by 1972, they thought they could do it. They also recognized, so by 1972, this is part of a regulatory story, is that the regulatory ground was shifting. We're entering a new era of regulation by the early 1970s. And so things are changing. And so risk assessment is going to offer them answers to new questions. It's also going to make regulators smarter. The industry is developing this stuff. If the regulators are going to keep up, if they're going to be able to stay on top of these new licenses, these new proposals for reactors, they have got to develop similar capability within the regulatory branch of first the AEC and then, of course, the Nuclear Regulatory Commission. So 1953. To tell you this story, I have to go back to 1953. Why did GE propose this? And to explain that, I have to tell you how they conceived of safety back in the early portion of the Cold War. How did Hanford make sure their reactors were safe? And what happened that GE suddenly said, let's go off and try to figure out what the chance of a reactor accident is? Okay, let's see if I can explain this. Today it's called the Advisory Committee for Reactor Safeguards. Back then it was called the Reactor Safeguard Committee. It's a body of experts who analyzed reactors, looked at their safety, especially new reactor proposals, and evaluated whether they were safe enough. They launched a major effort to do this in 1948. By this point, the AEC has got reactors going up around its system of national labs. And Edward Teller is the chairman of the Reactor Safeguard Committee. Teller's an interesting figure in this because you look at him, he has a very conservative approach to reactor safety. He's always writing letters to GE saying, can't you make these accidents impossible, using the word impossible? Can we get a foolproof device to make these reactors safer? That's kind of, Teller, so Teller really was concerned about reactor safety. But what I want to tell you about is, how did the Reactor Safeguard conceive of safety? Because we're going to move off of this. There's 4 layers, what is often today referred to as defense in depth. They didn't use that term back then, but this is pretty much it. Involves 4 kind of layers of safety, okay? Citing inherent safety, static layers, active systems. I'll try to explain. That's citing. Safety for the Hanford reactors was largely ensured by all of that sagebrush out there. Sagebrush and rattlesnakes. I lived in Eastern Washington, I know. Okay. For the public, anyway, safety at the Hanford reactors was that isolation, the huge Hanford expanse. The early estimates of how far radiation would spread if there was a kind of explosive release of energy was about 1.5 miles. No problem. Hanford was bigger than that. So they spaced the reactors more than 1.5 miles apart and had a very, very large reservation of land that ensured public safety. Now that doesn't help the people at the reactors, but that is how the public was kept safe. So that's siting. But you need more than that. After all, Hanford reactors did not have this inherent safety. It's called today a positive coefficient of reactivity. If energy rises and starts heating up the reactor, it's almost like a gas pedal. The power starts to surge upwards. Commercial plants today have a negative coefficient of reactivity, which is supposed to retard any possible surge in power. Okay? But Hanford reactors didn't have that. And that concerned the Safeguard Committee. But they said this is to avoid this is in fact a test of, they did a number of tests on light water reactors to see how stable the reactors were, to various runaways. And this is where they actually initiated one by ejecting rods out of the core and the like. So inherent safety was something that was missing, and this concerned the Reactor Safeguard Committee about the Hanford reactors. In fact, they said the Hanford reactors pose a degree of risk which, in the opinion of the committee, is greater than any other existing reactor plant. So they want safer reactors. Of course, static layers, that's it. Steel shell, containment buildings, boundaries, physical boundaries that will hold in the escape of pressure from a steam leak or anything like that that will prevent radiation from getting out. Very reliable. All these first three that I've mentioned are very reliable systems, right? I mean, sighting is basically guaranteed. If you design the physics of a reactor so that it has a negative coefficient, that's about as good as you can get. Containment buildings aren't quite as reliable, but, pretty good. More than pretty good. And then there's active systems. Of course, to protect the personnel and the reactors themselves, you needed something that was going to shut down the reactor as quick as possible. This is a drawing of the Chicago pile. Okay. 1942. The first active shutdown system was a guy named Norm Hilberry, who held an axe in his hand, and if things were to go wrong, he was to swing the axe, cut the rope. You can see that thing called the zip rod. That's a control rod that's going to absorb the neutrons and shut down the reactor. Okay? Hilberry was the first active safety system. All he had to do was swing that axe, rod drops in, reaction stops. That was the design. Now, people think that that was where the term SCRAM comes from. Supercriticality reactor axeman, or stop criticality reactor axeman, or start cutting the rope right away man. That's not where it came from, but that's a different story. If we have time, you can ask me about that one later. Okay. Active systems, they're great. They stop the reaction immediately, but they're the least reliable. Hilberry has a heart attack. He forgets to sharpen the axe. He swings and misses. All probabilities that you have to accept are possible. So for the Safeguard Committee, active systems were important, but it's not what you went to the bank on. What you went to the bank on was that isolation out there, that sagebrush. But they went and decided that the original estimates of how far radioactivity could spread during an excursion of the reactor was probably too low. They came up with this equation. Square root of power times 0.01 is what your exclusion zone, nobody in it, zone should be. For those reactors, that was about 5 miles. For today's, if we use this for civilian reactors, and you don't because this was actually designed, this equation was designed for the Hanford reactors. But if you use that today for modern reactors, bigger ones, it would be a 17-mile exclusion area. We just don't do that today, which is why we use all of those other safety components as well to get at a degree of safety. But for the Reactor Safeguards Committee, this was important. You didn't really have many other safety devices at Hanford. All you had is isolation and you had active shutdown systems. And that was it. But there's a problem with this equation, and GE figures it out very quickly. They apply the formula to the existing reactors. Here you can see the Columbia River flowing through it. The little square shaded areas are the reactors, and they started drawing circles around the reactors. You see that stair-step line up above the north of the Columbia River? That's the boundary of Hanford. And so the circles were moving out beyond their property. And as you can see there, it actually covers the town of Corfu. That's kind of a generous term for Corfu. It's basically a post office number. But the boundaries are growing. And so the Safeguard Committee realizes that you don't have isolation. You don't have that first boundary. And so they go to GE and they're saying, you got to come up with some sort of device that's going to make these kinds of excursions, these kinds of explosive releases, impossible. GE comes back and says, we can't do that. You can't come up with a design that's going to prevent this. The reactors are what they are. In 1953, GE proposes a new kind of approach to safety. They said a disaster was the culmination of small malfunctions and mistakes. While there have been no disasters, there have been incidents which, in the absence of mechanical safety devices and or the alertness of other personnel, could have led to disasters. A disaster will consist of a chain of events. It may be possible to evaluate more specifically the individual probabilities in the chain and then amalgamate these results to obtain the probability desired. 3? Oh, okay. So that recognition of that they didn't have the safety they wanted meant that they needed to try a probabilistic approach that would basically say that the risk was low enough. The Safeguard Committee had actually said what they thought was safe enough, 1 million to 1. For reactor accidents, about 1 million to 1, that's probably what most people would be happy with. Hold on to that thought, because we come back to 1 million to 1 often. Okay, so because GE tries to do this, but they discover they can't. It's just too hard, it's too complex, there's no data. Safety in the commercial world is going to be basically determined by these three, the 3 Ds of safety: design basis accidents, maximum credible accidents, deterministic design, and defense in depth that I just described. Maximum credible accidents are the worst accidents that you think are likely, or possible, I should say, within the life of a plant. Deterministic design is you pick components, safety structures, and design systems that you think will prevent that. There's nothing really quantitative about this except that some engineer said this accident is something we should design against. And defense in depth creates the barriers that will prevent that accident. And those are the... But what's going to happen is as we move into the 1960s, is there's going to be a turning point in regulation. And in 1967 that I'll get to. And this is going to require new approaches to safety. The 3 Ds are going to need to be supplemented with other approaches to safety. The first time that the AEC tries to estimate the consequences of a reactor accident is in 1957. It's called WASH 740. And it came up with an estimate that the worst hypothetical accident would kill about 3,400 people. This was not good news. The AEC tried to contextualize this by talking to experts and saying, how likely do you think one of these accidents are? And they got all kinds of responses, but most of them focused on about a 1 in a million chance. Some said 1 in a billion. Some refused to offer a guess because they said putting out a number gives respectability to the whole process of guessing at a number that you really can't calculate. But this report becomes a cross that the AEC has to carry for years afterwards. And it becomes a major problem for them. Critics cite it all the time. The AEC wants to kill it. And in 1965, Congress asks the AEC to go off and do it again. The AEC said, this is a bad idea. We don't have any new data to determine to do anything that's going to really be different about the original study than what we have now. There's nothing new that we know that's going to change things. Congress said, well, go off and do it anyway. And since reactors were bigger, the consequences were bigger. That was basically the difference between the first study and this study. Those numbers were so high that the AEC refused to publish the study. And it became a kind of open secret that it existed. They also went off and tried to get companies that they had developing probability estimates to see if they could come up with a halfway decent estimate of what an accident would be like. By this time, they actually had some people working on this problem. And the company that came back and said, well, if you use operating data, it's about 1 chance in 500 operating years. That's not a good number. If you're planning on building 1,000 reactors, 1 in 500 is not useful. But it just reflected the fact that they didn't have enough data to do this. They also came up with a failure chain estimate. Those numbers were up around 1 in 100 million to 1 in 10 quadrillion. Okay. That is 700,000 times older than the age of the universe. Okay, so these were really wildly off numbers. Everybody knew it. And so the regulatory branch is really opposed to doing these kinds of studies going forward. They're very, very wary of them. But others are working on it. The curve on the left is what the British were working on. This is kind of a safety goal. You see reactor years of accidents, and on the right you see Curie's. So this is, again, a probabilistic approach to safety. They were going to design the reactors to stay under the curve, a quantitative approach. The one on the left is put together by a guy named Chauncey Starr, and here he specifically recommended, let's develop quantitative numbers and use it to compare to other kinds of risks in the world. This is in the late 1960s. I'm going to skip over, unfortunately, Steve Hanauer. Regulatory branch resists these efforts. They say, look, we've tried this before. It's really not something we're ready to do yet. But two things are going to change their thinking about this. One, the China syndrome. That accident isn't just a movie. It's what can violate a containment building if a core meltdown occurs. And so the China syndrome was something they had to deal with. If the containment isn't really going to work like they thought, you need other systems to prevent a major accident. And the AEC was going off and they were trying to develop a test of a core accident. They actually had one planned out in Idaho. And that's what this drawing is. They're actually going to build a reactor, start it up, run it for a long time, have a loss of coolant accident, and stand back and watch what would happen until they realized that and so they changed it. But the crisis over recognizing that this could violate containment meant they didn't have one of their layers of safety. In steps GE, remember them from Hanford? They were the ones who promoted a probability assessment. They say we need to shift toward a probabilistic approach to safety. And they promote this in the late 1960s and early 1970s. They're focusing on the reliability of systems. And they're saying our systems, the way we're designing them, are reliable enough. And so that thinking about reliability begins to percolate. The AEC does not buy the idea of using probabilities. But they accept the idea that these systems, these active systems, are now reliable enough that they can be relied on. So we move from a reliance on containment to emergency core cooling systems and other active systems to ensure safety. I'll also skip over, unfortunately, the next one, which is anticipated but there's a number of safety issues that come up that really require a kind of look at probabilistic approaches to safety to help them understand accidents that were outside of the boundary of maximum credible accidents. There was a number of them that were popping up, things that had not been designed before. The other problem that's emerging in the late 1960s, early 1970s is the anti-nuclear movement is becoming more powerful. They are questioning this approach to safety using emergency core cooling systems. There's a number of hearings. And so movement is pushing on the AEC. EPA actually wants the AEC to use probabilistic estimates for environmental impact statements. They're saying, look, you're saying that these big accidents are really unlikely. So you better prove it. And if you don't do it, we're going to do it. Okay. And finally, Congress is also pushing the AEC to really prove that reactors are safe. I'll skip over that one too. WASH 1400 is launched, therefore, in 1972 because there was a regulatory crisis that was emerging. There was a political crisis. But they were also beginning to recognize that risk assessments could help them solve some of these safety problems that they're dealing with. It's a combination of technical capability and the recognition that probabilistic risk assessment can get at problems they had not considered before. All right. Okay, I'm going to have to skip Dixie too. One of the things WASH 1400, as I mentioned, did is it actually got at accidents that people didn't realize were even a major problem. This boring of entry is for a small leak. They came back and they said, you know, the accidents that are really pose a greater risk than these big pipe breaks are little ones. They require different kinds of safety systems. These really need to be looked at in a different way than we have in the past. So they were basically pushing to expand the number of accidents that were being looked at. The problem, of course, as I mentioned, is that these error bands that they came up with for their numbers were really high. Do you see that part that says revised 2? the Unit of Concerned Scientists, an anti-nuclear group, basically showed that if you combine some of these potential errors, the odds of a reactor accident could be much higher than what the report said. And that critique ultimately stuck pretty well and forced a revision of WASH 1400. Okay. So the positives were some of the things I've already mentioned: new methodology, broad range of accidents. They found that meltdowns were more likely, but consequences were less. The negatives, as I mentioned, large error bands, some of the comparisons they made, you couldn't compare this to meteorites, you couldn't compare it to hurricanes and tornadoes. It lacked adequate peer review, and ultimately, the study, at least it seemed, was going to be that the NRC was going to walk away from it because of the kind of embarrassing revisions that needed to be made. 3 Mile Island, however, in many ways, people argued, validated risk assessment. It had pointed out some of the things that actually occurred at 3 Mile Island, that human error was a major issue, that, as I said, things like small leaks, that's what 3 Mile Island was, could be a major risk in a reactor plant accident. Severe accidents needed to be analyzed more. And so the Rasmussen report ultimately gets saved as a reactor is destroyed. And these are some of the things that have been accomplished at the NRC. One other, I'm going to add on, but I'm going to need another 5 minutes or so. So what we see here is that risk assessment comes back into its own in large part because people begin to recognize that events are starting to prove some of the predictions that probabilistic risk assessment brought forth. So the NRC eventually develops quantitative safety goals in 1986. Risk assessment is applied to some mundane things like maintenance, actually a major success in risk assessment. And ultimately, a risk assessment, a probabilistic risk assessment policy statement is issued by the NRC in 1995. It's notable that the report comes out in 75, and the NRC actually doesn't put out a statement about what you should do about PRA for 20 years. That's how damaged that report was initially. It took 20 years to really develop a statement where the NRC actively encourages the use of risk assessment and what's called risk-informed regulation. So I've talked a lot about nuclear. One of the things I'm also working on is how did risk assessment affect other areas? How did this methodology get used elsewhere? And one of the agencies that's been affected by a risk assessment, they begin it, they walk away from it, and they come back to it, is NASA. And the Nuclear Regulatory Commission and NASA have worked together very well in recent years to kind of develop new approaches to risk assessment. This largely comes out of the Challenger accident. NASA helps develop some of the early fault trees, but it decides that fault trees don't work for them. It gives them bad results. And so they basically put it aside and use qualitative approaches to risk for most of the Apollo program and the shuttle program. And this is a kind of cumbersome thing to do with the space shuttle. They develop lists, critical lists of potential things that can go wrong, critical items lists. By the time of the Challenger disaster, these lists could have 2,500 items on them, and you don't know which ones are most important because they're not using probabilistic methods. And so by the time of the Challenger disaster, this system that they're using is becoming increasingly cumbersome. Famously, NASA, after the Challenger accident, their efforts at risk were really criticized a great deal. Their estimate was that a shuttle would fail once in 100,000 launches. That number was roundly criticized, most famously by Richard Feynman, Nobel Prize winner. He was involved in the review panel that looked at the space shuttle. And he famously kind of demonstrated how the O-rings would fail when they're cold. He takes a little clamp, sticks it in a glass of ice water, clamps it down, and the O-ring has no elasticity and therefore doesn't seal. But he also criticized their approach to risk assessment. He basically said, where did this 100,000 number, this is a management failure. They're completely disconnected from the possibility that this rocket could fail. The number he said the number was, basically, he said their number was so high, he said it was like, they were like playing Russian roulette was his term. That every time they had a successful launch, they basically spun the chamber again and tried again. They had no idea how close they were to disaster because they didn't understand risk, because they weren't using probabilistic methods. The interesting thing that I found about this is that in some ways, I'm not sure he's being fair to them. If you look at other agencies and their estimates of risk, they routinely said 1 in a million. NASA was kind of a pessimist. Even the Supreme Court came up with 1 in a million, right? So, so my point is here is that untethered to any kind of risk assessment, you tend to revert, it almost seems like it's in our genes or something. We love 1,000,000 to 1. And that, one person described it as the search for the Holy Grail, that 1,000,000 to 1 risk. And NASA, so NASA, I'm not sure that this is a reflection of their management necessarily, as much as not using quantitative data to develop a probabilistic risk assessment when you can. And so let me go back to that satellite that I mentioned. There was actually a healthy debate going on. When the Challenger failed, there was a debate going on within NASA about whether the risk numbers they had were legitimate. And why was that? Well, remember how I said they did a probabilistic risk assessment of satellites? That was required. By presidential directive, you had to go off and do a risk assessment anytime a nuclear-powered satellite went into orbit. And so they were doing this one back in the 1960s. When they were going to launch nuclear payloads in the 1980s, they had to do them again. Now, this doesn't have anything to do, this is not linked to Challenger or their decision to launch. This is a debate that's going off on the side. And the reason I bring this up is that aerospace engineers, unconnected to probabilistic risk assessments, were offering up numbers like 1 in 100,000. Nuclear experts who reviewed their work said 1 in 100. And that debate was going back and forth heatedly. I mean, the numbers were flying around, 1 in 100, maybe 1 in 50, maybe 1 in 1,000. But NASA's saying, no, much higher, 1 in 10,000, 1 in 100,000, not really connected to any kind of probabilities. So I'll have to skip over these. But so ultimately, NASA does come back to, if you look to the bottom 2 lines, ultimately NASA will do in the post-Challenger era, develop a probabilistic risk assessment. Where do they get help? From the nuclear industry. In fact, they use a number of outfits that had done probabilistic risk assessments in the nuclear industry to do theirs. And they've hired a lot of people into NASA with NRC nuclear industry experience to develop a new approach to risk in the last 10, 15 years in particular. Okay. I'm up to 55 minutes. Should I? You would. Okay. Okay. I also wanted to talk about something else, how risk assessment was used as a kind of techno-diplomatic tool in the post-Cold War era. Here you see, on the left, the Soviet representative for nuclear safety regulation, this is after Chernobyl, signing an agreement with the Nuclear Regulatory Commission, Lando Zek on the right, a cooperative agreement. When the Russians came in 1988 to sign this agreement, they also came looking for our computer codes, probabilistic risk assessment. They wanted help on computer safety. That was something they lacked. When the Soviet Union came to an end, Central and Eastern Europe was filled with light water reactors designed by the Soviets that Western Europe was alarmed about for a lot of reasons. Their safety approach didn't match the West. And there were many calls to shut down a lot of those reactors. Some of them were in Eastern Germany were closed immediately. But in other countries, as Eastern European nations came to the West looking for help, financial help, and ultimately being integrated into the European Union, the West was saying, what are you going to do about these reactors? And ultimately, what I find is that there was a number of competing interests here. These countries want to keep the reactors going because, well, they got to keep the lights on. Western Europe, remembering very much the Chernobyl accident, is also intent on seeing the worst reactors closed down. And what I found interesting as I looked through the dynamics of how they sorted out which reactors would keep running and which ones would be closed, that one of the key tools that is used is probabilistic risk assessments, taken from, of course, the Nuclear Regulatory Commission, but by this time many nations were using it, and so they're getting help from many different countries. And they're using risk assessment. In Central and Eastern Europe, they're using it to protect their interests. They're trying to use it to demonstrate that these reactors can be shown to be as safe as Western reactors, or close to it. Or in the case, the worst reactors were actually were those considered in Bulgaria, which the Kozloduy reactors were considered to be unsafe, least safe of them because of operating problems and the like. And these ones were called on to be shut down. These were some of the oldest reactors. They didn't have containment buildings, and so people said you can't have reactors without containment buildings operating, not if you want to be in the European Union. But Bulgaria is actually able to use risk assessment to kind of slow down the process. These reactors don't get closed down for over 10 years before they're finally closed once and for all. But because they were the oldest and considered the least safe, eventually they are closed. Just to use another example of how risk assessment was used both by the West to verify that these reactors were safe and by the former communist nations to demonstrate that they should keep these reactors running, is Temelin in the Czech Republic. This reactor was kind of a weird design. It's a Russian light water reactor, but to satisfy the West, they go off and the entire electrical system was purchased from Westinghouse. So it's called an Eastinghouse reactor. But the idea was they used this and then they plugged this all into a probabilistic risk assessment. In Czech Republic, Austria was dead set against these reactors coming in with the Czech Republic into the European Union. They were able to basically say, no, these reactors are safe enough. We've done the risk assessments. They compare favorably to Western reactors. We're going to start them up. And they did. So this was a way, risk assessment became a way of kind of sorting out the blessed and the unblessed reactors in this period. This is kind of a case where you see where technical expertise helps solve what was really a diplomatic problem in many ways, sorting out the interests of Eastern European nations and the West and what they wanted as far as safety goes. Okay, and so with that, I would note, so PRA has been a success in a number of areas, regulatory. The one thing I do want to point out, I think the part that failed was that goal of using PRA to compare it to all these other risks. What Chauncey Starr wanted was to be able to take a nuclear power plant and compare it to bicycle accidents and coal plants and the like. We never really get to that kind of numerical, plug it into a graph and be done with it. Okay, I'll stop there.
Thank you very much, Tom. So we have time for questions. I'll pass around the microphone.
Do I need to name it? Okay. Ready? Hi, my name is Toshi Higuchi from Georgetown University. I'm also a historian, so I'd like to ask you to go back farther in time, and then because I wonder if there is any direct or indirect connection between the GE's interest in the probabilistic risk analysis with the operations research during World War II and the systems analysis that came out of it. Actually, my research is about the biological effects of radiation, and then I found a direct connection in terms of the personnel as well as the kind of tools between the OR and then the health risk assessments of radioactive fallout in 1950s. I wonder, in this case, I guess it's more about the military-industrial complex that really developed the tools during the World War II and the networks among the engineers and others. But I'm curious about where GE got the idea in the first place.
I'm going to have to disappoint you on the search for a link. If I had seen it, I would have loved to see it. I would have been all over it. I mean, the Hanford documents, you get the impression it's kind of self-contained effort on the Hanford Reservation. It's basically a dynamic between GE and the Reactor Safeguard Committee that's calling for efforts to develop safety. What I think it's more probably in line with is that at the same time in the 1950s, you are getting greater efforts in a host of other areas, and GE being an electrical company especially, reliability of components, reliability of electrical systems, and I think what GE really does a lot at Hanford is develop a focus on the reliability of an entire system. So this is in the water in the 1950s in other areas outside of defense as well. It's, some of the first reliability societies are actually founded in the 1950s, and it is in part developed with defense industry and the reliability of missiles. So certainly, but the weird thing is I don't see a lot of references to that. So it's kind of frustrating. I think it's there, but you don't see it in the memos. You don't see it in the studies that they develop at that time all that much. But I would agree. I mean, GE is a major defense contractor. They must have been, thinking along these lines.
So I wanted to encourage our online participants, if you have questions or comments for our speaker, please send an email to siren@vt.edu. We have one question from François Diaz-Morin. Hopefully I'm not butchering that name too much, who is a nuclear security visiting scholar at the Center for International Security and Cooperation at Stanford, and used to work as a mechanical engineer on the supporting analyses for the safety design of the US version of the EPR reactor. And his question is as follows. The adoption of probabilistic approach to reactor safety implies that risk is considered in terms of acceptability. Yet the definition of what is acceptable or not is something that can be done only through deliberation within society, because it's implicitly cultural, not technical. Therefore, how do experts in PRA deal with this dilemma when making the assumptions themselves over what should be considered as acceptable? Isn't this dilemma the source of the still active controversy over the use of quantitative risk assessment approaches for reactor safety?
Let me go back to WASH 1400. They were very aware, and they stated this repeatedly, that WASH 1400 was not making an overt policy recommendation, that was something that had to be done by the public. And I didn't mention this in the presentation. As we move into the period where the NRC is dealing with post-3 Mile Island issues, they're trying very hard to develop a model so that they can get feedback from Congress and the public about what is acceptable risk. I mean, they talked about that. On the other hand, I mean, when you look at WASH 1400, clearly they were trying to say, these are safe enough. They had a standard in mind, and I think that's what got them in trouble in WASH 1400, besides the fact of the inaccuracies. I mean, there was a kind of standard in their heads, this 1,000,000 to 1 number that was so common at the time. So how do we do this going forward is a hard question for an historian to answer. But they did, engineers in the 1970s and 1980s said that over and over again. This is a policy decision that has to be made by the public or by its representatives in Congress. There wasn't a lot of direction from Congress. Eventually the NRC, with its safety goals in 1986, developed something that they're trying to actually kind of make create a model that Congress could, look at. Basically, so they're taking the initiative. But there was a long discussion in the 1970s hoping that Congress would provide direction in this area. So I know that doesn't answer the question, how do we do this going forward? But it was certainly, they were hoping for direction. in the 1970s and the 1980s.
Any other questions, comments? Yes? And please introduce yourself. Please introduce yourself.
I'm Doug Chapin. I'm an engineer and have been in the business a long time. And I don't disagree with what you said and the analysis and the like, but to me, the key to solving the problems is you use these kinds of analyses and you identify issues that have to be dealt with, and then you have to go and do something about them. And when I first started as an engineer, I was in the Naval Reactors program. And Rickover's rules were, if something happens on the ship, then we look at what happens on the ship and we see what we have to do to fix it. And you carry that all the way forward to the situation in Japan at Fukushima. And it was not a question whether or not those plants were designed or people didn't know what needed to be done to make them safe. It was they didn't do what they needed to do. They had never trained the operators to deal with the accident that they had to do. They hadn't looked at dealing with failures in the equipment that occurred. They had never worked with the government to set up what they were going to do if they had a crisis. And so to me, I think a big part of this fixing the problem goes to not only doing what you're doing here, which is correct and needs to be done, but then as you identify things, you look at the plant and you say, gee, if this happens, then the operators have to act. Then you say, have we trained the operators? Are they knowledgeable and can they do this? And if they're not, it's not safe and we need to fix it. So to me, that's another big piece of this is the implementation of the actions that this process is telling us we need to deal with. And I don't think this process necessarily tells us what the actions are, but it's very effective at telling us what the issues are that we need to deal with.
That second era of regulation that I talked about, one of the things that really becomes predominant in that period is that regulators start to focus on exactly the things you're talking about: operations and training operators, operator actions, having integrating human beings into defense in depth, basically. That these other layers, help us, operate these reactors better. Before, the China syndrome and other problems, it really was a design problem. If you go all the way back to the Hanford reactors, it was a siting problem. So we've kind of moved forward and expanded how we deal with safety issues, drawing on these other kinds of resources to make reactors safer. And as you point out, of course, Rickover had a huge emphasis on the involvement of human beings in ensuring the safety on the submarine. Who else were you going to rely on?
I agree with you.
Yeah.
You take 3 Mile Island, which I worked on. You take Chernobyl, which I worked on. You take Fukushima, which I worked on. All of those were things that we knew ahead of time. Fukushima was the wrong site. They were assuming they didn't have a tsunami, and historically that was invalid. And so they'd never done anything about the site. If we have a big tsunami, what's going to happen? We're going to have an accident that is awful. And with 3 Mile Island, we didn't have the operators properly trained. We didn't have the instrumentation done. So, we went back and we fixed a lot of those things. At Chernobyl, the same thing. The Russians had not thought through the situation that they created, what they were going to deal about. So I agree with you that figuring this all out as to what the issues are and what's important are crucial, and this is a big, important effort to do this, and I'm a user of the Rasmussen, and I've done a lot of these kind of analyses myself. But the punchline is you got to fix it. If your house is going to burn because there's something you can do in the house, then you and your wife and your children ought to sit down and figure out what you have to do so that's not going to happen to us.
Any other questions? Comments?
Hi, I'm Valerio Mascolino, and I'm a PhD student here at Virginia Tech in nuclear engineering. And I have a question which is somewhat similar to the comment that has already been made regarding actually how do you, in this probabilistic risk assessment, there is an issue which is some events, they don't have a high enough statistics to be accurately predicted. So whatever frequency you come up with, it's going to be very, very uncertain. And I think the events that have like shared this feature are mostly human error, which is very, very difficult to quantify, and natural events like what happened to Fukushima. And basically, if we think of all the big nuclear reactor incidents, they can be cut down to these two categories. It was either a human error, so the operator wasn't trained enough or didn't know what to do or hasn't ever seen anything similar like it happened in 3 Mile Island, or the natural events as happened in Fukushima. So what has been the effort during the years and even now to improve on that kind of statistics, especially the human-related one? Because, of course, the natural-related one depends on nature. But what has been the approach to have numbers, like statistical numbers, with respect to the human error that are more and more reliable? And after this, can you please tell us what the Scrum word comes from? Thank you.
Sure. I wish former Commissioner Apostolakis was here. I mean, he's done a lot of work. I mean, there's been a lot of work, especially after 3 Mile Island, trying to get better at understanding the role of human factors. It's interesting how far back that problem goes. The Rasmussen report really couldn't deal very well with sabotage. I mean, they brought this up. They understood that this was an issue. By the way, GE in 1953 couldn't figure out how to deal with sabotage, in part because they went to the Department of Defense and said, can you help us with this problem? And the Department of Defense said, no. I don't know why, actually. I'd love to understand why. Sabotage has been a major concern of reactor accidents all along, and yet, it's some of these issues are very difficult to get at. In some, if you're looking at just quantification, I mean, you just kind of add on another layer, a little kind of extra margin to account for some of these unknowns, but that's not an entirely satisfactory answer. But certainly, since 3 Mile Island, I mean, there's been a lot of effort to try to integrate human error into these risk assessments. I can't talk a lot about how successful it is because there's a lot of. It's still considered an area that needs work.
But how is it done? How is it done somehow? Because how do you actually get better statistics on how a human being behaves?
Simulator training.
What would you say?
Simulator training.
Simulator training, and actually, and I mean, there was a lot of financing of studies to look at human performance under various conditions that the NRC financed in the 1980s and 1990s. So, I mean, there is ways of doing it, but of course, the human element is always going to be the least satisfying as far as statistics go. Oh, Scram.
Yeah.
The short answer is. When you hit the scram button to shut down the reactor, you scram out of the building. That is where the term comes from. It's not, we love our acronyms, I know, in the nuclear industry, but this one isn't really it. It's really from the slang of the 1940s. Scram was a favorite word at the time. By the way, so is the term crud. That was also from the 1940s and has nothing to do with chalk river. If there's any Canadians in the room, I apologize. But those two terms were not really acronyms.
Any other questions? Yes.
Yeah, excellent talk, Dr. Wellock. Dan Miller, I'm a PhD student here at Virginia Tech in the Science and Technology Studies. Something that Doug talked about, or mentioned a bit about nuclear Navy. I noticed you talked quite a bit about NASA, but did you see any evidence in Navy personnel as far as, PRA, influencing anything for the regulatory piece?
No. Drove me crazy. I mean, I kept expecting it. It was, kind of like with Hanford. I was expecting that, but I don't see. Perhaps you can. I did not see evidence that the AEC did a lot of interacting with the Navy when they were developing the Rasmussen report. They went off and they got experts out of aerospace. They absolutely did that. They also pulled people out of the national labs, but I don't see interaction with the Navy. So if it was happening, it was not in the documents I see. That was one of the surprises about it. In fact, I remember when I wrote this article, one of the referees commented on that. Where's the Navy in this? And I said, well, I would happily put stuff in there, but you don't see interaction in this period with the AEC and naval reactors.
Anyone else? Questions, comments? All right, then please join me in thanking Tom for a great presentation and an interesting discussion.
Great job. I want to show you something. Flip to your slide, find them.
Oh, there we go.
Take a look at the reporter right behind you.
No way.
Way.
Really?
Yeah.
Holy crap. That's hilarious.
What was the revelation there? Yeah, that one. Same hairstyle. Different glasses.
Yeah.
Yeah. Seriously?
Yeah.
Oh, wow.
What was the event? I mean, in particular.
That was at the State Department when he was presenting his